Okay, section 29, Contravariant and Covariant Vectors. In this and the following sections, an introduction to tensor calculus will be given. The basic ideas are contained in this section, while the material in the following ones is only a simple generalization of those ideas. We will just introduce all concepts formally and later in section 32, which is vectors in a surface and the contravariant metric tensor. In section 32, we will treat geometric interpretations and relations to the theory of surfaces more in detail. In the preceding section, we investigated the behavior of the coefficients g subscript alpha beta of the first fundamental form with respect to an allowable coordinate transformation u superscript alpha, which I'll refer to as u alpha, equal to the function u alpha of u over bar 1, u over bar 2, where alpha is 1 or 2. We obtained the important formulae 28.3, which are the transformations between the first fundamental forms given by g over bar sub mu nu equal to g sub alpha beta times partial u alpha partial u over bar mu times partial u beta partial u over bar nu, and conversely g sub alpha beta equal to g over bar sub mu nu times partial u over bar mu partial u alpha times partial u over bar nu partial u beta. We will immediately see that this problem is a part of a more general one. The general problem will be investigated in the course of this and the following sections. In doing so, we will gain knowledge of the transformation behavior of all quantities, which will interest us in the sequel. We first repeat the fact that the inverse u over bar alpha equal to the function u over bar alpha of u1, u2, where alpha is equal to 1 or 2, of an allowable transformation exists and is of the same class as the previously given transformation. In this and the following two sections, we drop the restriction of the dimension n equals 2 and consider Riemannian spaces of any dimension n. See section 27. There will be no difficulty at all. Let u1, u2, etc. through un be the corresponding coordinates. Instead of the transformation u alpha, we have now to consider transformations of the form u alpha equal to the function u alpha, which is given in terms of u over bar 1 through u over bar n, where alpha can be 1 through n. And we assume that this transformation u alpha is of class r greater than or equal to 1, and that the inverse transformation u over bar alpha, similarly given by a function u over bar alpha in terms of u1 through un, where alpha can be 1 through n. This transformation exists and is of the same class. A transformation of this form satisfying these conditions will be called an allowable transformation. We assume that the allowable transformations to be considered form a mathematical group, which, to remind ourselves what that is, a group has the four following properties: associativity, identity being a part of the group, the inverses for each element being a part of the group, and the closure of the group. So more specifically, associativity is that parentheses work out as you would expect. If you have the quantity a plus b, closed quantity, plus c, where a, b, and c are elements of a group G, then that is equivalent to saying a plus the quantity b plus c, closed quantity. The existence of the identity element in the group is simply that you would have, if the operation were addition, let's say, then the element 0 would be a part of the group, so that you could have a plus 0, and that operation with the identity element 0 returns the original element a. You also have the existence of inverse elements, so that if you have a plus b, which then results in that identity element, then you would say that the element b is the inverse element with respect to the operation for the original element a. And you could denote them as a with the superscript -1, or you could, for the operation of addition, you could call it negative a and just have the minus sign in front. The fourth property of the group, of course, is closure. So for all elements a plus b, the result is itself a member of the group. You could call it capital G. So that's just to remind ourselves what a mathematical group is. To touch on some abstract algebra, which I know some of you guys in the comments have said you've wanted more of. It's hard to bring up abstract abstract algebra in differential geometry so far, as we've seen though. The summation convention must be slightly modified in this and the next two sections. Summations must be carried out from 1 to n, where, in the particular case of surfaces, n equals 2. If we write these transformation functions u alpha and u over bar alpha in the form u alpha equal to the function f alpha in terms of u over bar 1 through u over bar n, and similarly u over bar alpha equal to the function h alpha in terms of u1 through un, where alpha in each case can be 1 through n, we obtain the identities u alpha equal to the function f alpha in terms of h1 through hn, and u over bar alpha equal to the function h alpha in terms of f1 through fn. Now, if we differentiate with respect to u beta, the first of these two systems of formulae, we find partial u alpha partial u beta is equal to partial f alpha partial h gamma times partial h gamma partial u beta, where alpha and beta can be 1 through n. Since u alpha and u beta are independent if alpha does not equal beta, the value of the left-hand side of these relations is 0 or 1 according as alpha does not equal beta or alpha does equal beta. We therefore obtain the relations partial u alpha partial u over bar gamma times partial u over bar gamma partial u beta is equal to delta subscript a beta that itself has a superscript alpha, where alpha and beta can be 1 through n, and similarly partial u over bar alpha partial u gamma times partial u gamma partial u over bar beta is equal to delta subscript a beta that itself has a superscript alpha. Alpha and beta again can be 1 through n, where delta subscript a beta that itself has a superscript alpha is the Kronecker symbol, so delta equals 0 when alpha does not equal beta, or it equals 1 when alpha equals beta. In consequence of the elementary rules of partial differentiation, we have the following relations between the differentials du1, du2, etc. through dun of the coordinates u alpha and the differentials du over bar 1, du over bar 2, etc., du over bar n of the coordinates u over bar beta. Du over bar beta is equal to partial u over bar beta partial u alpha times du alpha, where beta is 1 through n. Hence, the differential du over bar beta is obtained by multiplying the differentials du alpha by partial u over bar beta partial u alpha and summing with respect to alpha from 1 to n. Conversely, du gamma is equal to partial u gamma partial u over bar beta times du over bar beta, where gamma is equal to 1 through n. We may say that the transformation function induces a homogeneous linear transformation on the differentials. The coefficients of this transformation are functions of the coordinates. An ordered system of n quantities which have the same transformation behavior as the differentials of the coordinates is called a contravariant tensor of first order, or contravariant vector. More precisely, we have definition 29.1. Let an n tuple of real numbers a1, a2, etc. through an be associated with a point capital P of an n-dimensional Riemannian space with coordinates u1, u2 through un. Furthermore, let there be associated with capital P an n tuple of real numbers a over bar 1, a over bar 2, etc. through a over bar n with respect to any coordinate system u over bar 1, u over bar 2, etc. through u over bar n, which can be obtained from the coordinates u alpha by an allowable transformation. If these numbers satisfy the relations a over bar beta equals a alpha times partial u over bar beta partial u alpha, where beta is 1 through n, conversely a gamma equals a over bar beta times partial u gamma partial u over bar beta, where gamma is equal to 1 through n, we say that a contravariant tensor of first order or contravariant vector at capital P is given. The quantities a1, a2, etc. through an and a over bar 1, a over bar 2, etc. through a over bar n are called the components of this vector in their respective coordinate systems. This vector will be denoted by a alpha or a over bar alpha in the respective coordinate system u alpha or u over bar alpha. The contravariant transformation behavior given by these relations is indicated by a superscript. The relation for the second given contravariant tensor can be obtained from the relation for the first given contravariant tensor by multiplication by partial u gamma partial u over bar beta and summation with respect to beta from 1 to n. In consequence of those Kronecker symbol relations given earlier, we find that partial u gamma partial u over bar beta times a over bar beta equals a alpha times partial u over bar beta partial u alpha times partial u gamma partial u over bar beta equals a alpha Kronecker symbol delta subscript alpha with itself a superscript gamma equal to a gamma. Since the notation a alpha occurring in the definition for the contravariant tensors is nothing but an abbreviated notation of the system a1, a2, etc. through an, we may also write a lambda or a tau or choose any other letter as index. Any set of n real numbers may be taken as components of a contravariant vector at capital P with respect to the coordinates u1, u2, etc. through un. The components of this vector with respect to the coordinates u over bar 1, u over bar 2, etc. through u over bar n are then determined by these contravariant transformations. The relation of this concept of a vector with that introduced in section 3 will be considered in section 32, which is on vectors in a surface and the contravariant metric tensor. In general, the quantities a1 through an and the corresponding quantities a over bar 1 through a over bar n will be given not only at a point but in a certain domain capital D of the space, that is, they will be functions of the coordinates defined in capital D. Then we say that in capital D, a contravariant tensor field of first order or contravariant vector field is given. For the sake of simplicity, we will use the name tensor instead of tensor field in this case also. While in the special case of Euclidean spaces, the free vector is the appropriate concept, in the general case of a Riemannian space, the concept of bound vectors is appropriate. The reason for this difference lies in the fact that, in general, the allowable coordinate transformations given earlier, in contrast to those in section 3, which are the vector x is equal to the sum on the index k from 1 to 3 of coefficient a sub I k times x sub k plus b sub I, such that the sum on the index I from 1 to 3 of the coefficient a sub I k times the coefficient a sub I l is equal to the Kronecker symbol delta sub kl equal to 0 when k does not equal l and 1 when k equals l, and namely that the determinant where each of the columns are respectively a sub I1 and then a sub I2 and then a sub I3, this determinant is equal to 1. So in contrast to that kind of a coordinate transformation, these sorts of allowable coordinate transformations are nonlinear, and the derivatives occurring in the functions for these transformations therefore depend on the coordinates, while the coefficients a sub I k given in the preliminaries section are constants. We will say that a geometric object is given at a point capital P of a Riemannian space if the following conditions hold. 1. With respect to every allowable coordinate system, one and only one ordered system of capital N real numbers is given. These numbers are called the components of the geometric object in the respective coordinate system. 2. A law is given which permits the representation of the components of the object with respect to a certain coordinate system in terms A of the components of this object with respect to any other coordinate system, and B of the values at capital P of the functions involved in the corresponding coordinate transformation and their derivatives. Geometric objects can be divided into classes. Each class consists of objects having the same transformation law. We already know two important classes of geometric objects. 0. Scalars or invariants are geometric objects with one component which is invariant with respect to any coordinate transformation. 1a. Contravariant vectors are geometric objects with n components which transform according to a over bar beta equals a alpha times partial u over bar beta partial u alpha, where beta can be 1 through n, and conversely a gamma, which is equal to a over bar beta times partial u gamma partial u over bar beta, where gamma can be 1 through n. Further classes will be introduced below. Another transformation, the so-called covariant transformation, is as important as the contravariant transformation, which was given previously. Its importance can be understood by the following consideration. We start from a simple example. The first fundamental form, ds squared equal to g alpha beta times du alpha du beta, is an invariant with respect to any allowable coordinate transformation. See the section in the previous stream, section 28. This form contains contravariant quantities, namely the coordinate differentials whose transformation behavior is known. See above. We now have to ask how the quantities g alpha beta must behave under a coordinate transformation in order that ds squared be an invariant. In the special case of the first fundamental form, the answer to this problem has already been given in section 28. But we may consider this problem as a part of a more general one, which we will now attack, starting from the simplest possible case. Let I equal b sub alpha a superscript alpha. Let I be a linear form of the components of an arbitrary contravariant vector a alpha and assume that capital I is invariant with respect to any allowable coordinate transformation of the form u alpha, or u over bar alpha. Denoting by a over bar beta the components of the vector with respect to the coordinates u over bar 1, u over bar 2, etc. through u over bar n, we have b over bar subscript beta times a over bar superscript beta equals b subscript alpha times a superscript alpha. We can easily find relations between the coefficients b over bar sub beta and b sub alpha of the form in the two different coordinate systems. In consequence of the previously given allowable transformation, we have that a alpha equals a over bar beta times partial u alpha partial u over bar beta, where alpha can be 1 through n, so that we have b over bar sub beta times a over bar superscript beta is equal to b sub alpha a alpha equals b sub alpha times a over bar beta partial u alpha partial u over bar beta. This relation must hold for any arbitrary vector a alpha. Hence, by comparing the coefficients of corresponding components a over bar beta on both sides of this formula, we find the following relations between coefficients b alpha and b over bar beta of the form capital I in the respective coordinate systems. B over bar sub beta equals b sub alpha times partial u alpha partial u over bar beta, where beta is 1 through n. Conversely, by the previously stated allowable transformations, b sub gamma is equal to b over bar sub beta times partial u over bar beta partial u over bar gamma, where gamma is 1 through n. And this can also be obtained from the previous relation by taking into account the previously given relation involving the Kronecker symbol. We now arrive at definition 29.2. Let an n-tuple of real numbers b1, b2 through bn be associated with a point capital P of an n-dimensional Riemannian space with coordinates u1 through un. Furthermore, let there be associated with capital P an n-tuple of real numbers b over bar 1, b over bar 2, etc. through b over bar n with respect to any coordinate system u over bar 1 through u over bar n, which can be obtained from the coordinates u alpha by an allowable transformation. If these numbers satisfy the relations previously given, we say that a covariant tensor of first order or covariant vector at capital P is given. The numbers are called the components of this vector in their respective coordinate systems. The vector in the coordinates u alpha will be denoted by b sub alpha. The covariant transformation behavior previously given is indicated by a subscript. This definition is again the definition of a vector bound at a point. We have already mentioned the fact that the tensor calculus is a useful tool in physics. In order to illustrate this, we consider the following. Example: if u1, u2, and u3 are any coordinates in space R3, the work done by a force as a result of an infinitesimal displacement du alpha is given by the expression d capital W equals p sub alpha du alpha, where p sub alpha are the components of the force with respect to the coordinates u alpha. The work d capital W is independent of the choice of the coordinates. Since du alpha is a contravariant vector, the force vector must be covariant for d capital W to be an invariant. A real function phi of u1, u2 through un, which is defined in a certain region and whose value is invariant with respect to all allowable coordinate transformations as previously given, is called a scalar function. The gradient partial phi partial u alpha of a scalar function phi of class r greater than or equal to 1 is a covariant vector, since partial phi partial u over bar beta is equal to partial phi partial u alpha times partial u alpha partial u over bar beta, where beta is 1 through n. Indeed, this transformation behavior is of the form previously given for the covariant transformation. And now we arrive at section 30, so I'm going to pause there and we're probably going to start a new video. See you guys in the next one. Peace.